Okay, good morning, everyone. It's 5 past, so we should probably get going. I'll just quickly share my video again just to say good morning to everyone properly. So I hope you've all had a chance to have a think about what we've been covering, give you a chance to absorb it, I suppose. It's quite a lot of material and we are going through it quite quickly, so I hope it's not too overwhelming. Um, with I think we will start off. We were going to look at. I said, I suggested to everyone that take a look at the very final challenge on the section we finished on Monday on derived types. So we'll do that, and then I'll just give everyone a chance to, if anyone wants to ask any questions at all about anything that we've been doing up to this point, anything at all from Monday and this little challenge, that would be a great point to do that. If necessary, we can have a discussion about anything, and then we'll make our way through today's material. And as we'll see, that really is object-oriented Fortran now. That's really what we are building towards. So we're doing something which I think a lot of people out there don't actually even realize Fortran is capable of at all. A lot of people who still think Fortran equals Fortran 77, if you say to them, no, I've learned how to do object-oriented Fortran, this would be surprising, I think, to a lot of people, but it really does have that capability, and that's what we'll be learning today. So, without further ado, I'll stop sharing my webcam to save some bandwidth and start sharing my screen, and we can move right on with that little exercise. Now, let me just share that screen. Okay, brilliant, that's coming through. Okay, so let's just quickly remind ourselves what we were doing. I hope all of you have been able to have a go at this. If you haven't, don't worry with us, and we'll just quickly go over what we were building up towards. So we had 2 pointers we were using, an array type, my array t, which had inside it an allocatable array of reals, and also my pointer t, a derived type, which instead contains a pointer to a real array. So remember, these are similar but subtly different in that if you make a copy of the allocatable array, then you get a deep copy of everything that's in there. A new array is allocated for you, and the values copied into it. Whereas if you make a copy of a derived type containing a pointer to a real array, instead you get a shallow copy, and the pointer in the new derived type instance that you've created simply points back to the array that was in the original that you were copying from. So they look similar, but under the hood, they're actually pretty different. What we also saw, in particular down here, when we were doing this exercise with it, we were trying to build it, what we found was that if you tried to make an assignment between a myArray type on the right-hand side and a myArray pointer type on the left-hand side, what you got was an error. So the compiler came back and said, you can't convert type myArray t to type myPointer t. We then saw at the very end of Monday that it is actually possible for us to define our own operations. We will be talking a lot more about this in a few minutes, but what we're talking about just now specifically is assignment. So we can define assignment operations using the equals sign, the same as any other intrinsic type that we've used to this point, like integers or reals. We can create our own assignment operation using a function that we ourselves write. So that the compiler might say, hold up, sorry, I'm giving you an error because I don't know how to convert a myArray pointer type into a myArray type, or vice versa. But we can turn around and say, that's all right, I know how it should work, so I'll write that as a subroutine for you, and then you know how to do it. And that was what our exercise is. We were asked to explicitly, the slight typo I'll have to go back and fix. We'll have to found that we want to make this explicit in that we can take the one and assign it to the other. So what we need to do is add a subroutine, just like this, and then tell the compiler that that's to be used as an assignment operation. So let's just quickly take a look at how we do this. So here I am back in my terminal. If you haven't had a go at this yourselves, I would say please do now try and follow along. Muscle memory, I think, when typing this out is actually something we build up, so it's worthwhile just having a go at this. So I'll head back into the usual spot inside that Git repository that we cloned containing everything, and go into section 4 on derived types. And I've still got some things here lying around from Monday, but the ones that we want are our example 2.f90 and my array type.f90. So here are those two programs, and in fact this is the state that it was in when I showed how this operation on the left at the moment, C equals A, fails. The compiler doesn't know how to set C equal to A. It was fine doing this, just saying, okay, C n length is equal to A n length, and C values points to A values. It was happy doing that, but if we said take C as a whole and assign it whatever is in A, that wasn't good enough for it. So what we've got to do now is go over to our module, and let's first of all write the subroutine that we're going to do to use this allocation. So let's just write a subroutine, and subroutines for allocation, and as we'll see in the next session, functions for other operations like addition, for example, or multiplication, they always have to follow the same format so that the compiler really understands how to do it. So for assignment, we've always got to give it 2 arguments. So let's just quickly give it a name. Let's call it assign array to pointer. There's probably a better name that we could give it, but for the sake of it, let's just call it that. Subroutine assign array to pointer. Those are the 2 arguments, and these correspond to the left-hand side in A and the right-hand side in B. And these are both going to be of the type that we want to use for the assignment. So the right-hand side, so the left-hand side is a my array pointer t, and that has to be intent out, because whatever it was before, it doesn't matter now. We are assigning B to it. So A is intent out. Then we want to type, and this should be a my array t, and this needs to be a target. In this case, we need to give it that target, because remember what we're doing is we're actually assigning a pointer inside this to a component of this, and that means that we need to make sure that this is a target type, and we can give that intent in, and that's intent in. We can place that that restraint on it, because we are absolutely certain that when we do A equals B, nothing at all should be happening to change B. B should be left completely unchanged. What do we put in it? Basically this that we did on the left-hand side. nlen should just be a copy. So a percentage nlen, we can say is equal to b percentage nlen. And then the values, well, we know that all we want to do is have the pointer inside this points to the array inside this. Again, that's why we added target to it. So let's do a percentage values points to b percentage values. and then we'll end that subroutine. Assign array to. Some of you, I just to say, like I'm bothering here. I'm taking the time to name all of my end subroutines and the like. Not everyone does that, and of course that's perfectly fine. You don't have to do that. I just like to do that personally, because otherwise, if I just see end subroutine, I go in my mind, I go, okay, which subroutine is actually ending, and have to scroll back to find it. It's a bit more here, but for me, it's just practice every end subroutine, end function, end anything. I tend to put the name of what is there alongside it. Practice, that's good working practice. Yeah, I would agree. Not everyone does it. I would recommend it still to everyone. I think it makes for, you know, it's a little bit more verbose. I don't think that's a bad thing at all. I think it probably in the long run helps people avoid bugs and just understand their code. If you're coming back to code after a while, it just helps you read it a little bit quicker. Okay, so that's good. So we've got our we have our subroutine. Excuse me. Now we just need to tell the compiler that it's actually allowed to use this this subroutine as an assignment operation. And to do that, we just create an interface, just as we did here, exactly like this. So interface, and we say we use this this particular little bit of syntax where we say it's an equals, it's an assignment, and I'll end the interface right away. And we say module procedure. Module here, strictly speaking, is optional. What we're doing here is we're telling the compiler that that this interface for this procedure actually exists within the same module right now. If you don't put module, then what you're saying is it could be outside a module somewhere. You might need to generate an interface for it. It might need one. But here what we're doing is we're saying, don't worry, it already exists. It's here. It's inside this same module, which probably, again, good practice is what you should be doing anyway. And then I called it assign array to pointer. So let's just do that. Assign array to pointer. Oh, I spelled pointer out in full. Okay, let's just make it match. So module procedure assign array to pointer, and let's write and quit everything. And oops, then what I didn't do was change example to .f90. Okay, so this didn't work before. C equals A. If I've done that at all correctly, it should work now. So let's try ftm my array type .f90 and example to .f90. And that compiles, brilliant. And if we run it, that seems fine. So that works. So at this point, we would want to see C matching A, and we get the values in it. We get 3, it has a size of 3, it is assigned, and the values in it are 1, 2, and 3. So that works as it should, just because we added that little bit of slightly odd syntax. Do we need to consider the destroy? In which way? This was, I think this was just showing. So this was showing something else. This was showing here how when we destroy the underlying array that was set inside A, the pointer to it that was living inside C is still counted as being associated, but the values in it disappear and become garbage. So again, yes, you would still want to do that. You would definitely need to code around this and make sure that whenever you destroy some array that pointers are pointing to, you probably want to have some way of nullifying those pointers at the same time, or otherwise marking them as being or marking the type as a whole as being invalid. However, that doesn't have anything to do specifically with the assignments that we were talking about. Can you determine which pointer points to an array? Yes, you can. So let me quickly grab something. Do we have I thought I had a link to this, but apparently not. But if you add to yes, exactly. If you add to associated an extra argument, which is the target, it will tell you specifically, is the pointer pointing at this target or not. So yes, that is the way to. I thought this was in the material. I'm just looking back at it, and I can't see that it actually is. That might be something to add in the future. But yes, you can do that. So that's a nice way to, you know, if you want to be very careful, you can add guards doing that. No problem at all. Okay, so I think that's us finished with that. Does anyone have any questions about this before we move on to new material? Anything at all, either about this or any of the material that we covered on Monday? I'll move on to the next page while people have a think. And if there is anything you want to ask, now is a really good moment to do it. Of course, you can ask whenever, but it seems like a nice sort of breaking point before we head into proper object-oriented stuff today. Okay, I don't see anything coming in. If you do think of anything, please just put it in the chat now, or maybe when we stop for our first break, 11:30ish or so. Otherwise, let's carry on with this new session. So what we're going to be doing here is we're going to be extending what we saw in the previous session just now. So what we actually were doing there is we were using what's called a generic interface. So when we said, let me quickly just grab, oops, when we had in our my array type, when we had this interface assignment equals, this is what's called a generic interface. And that has a number of different forms which you can give it. You can say it can be an assignment, or it can be a generic procedure name. It can be an operator, so something like addition, multiplication, finding the maximum or the minimum. All of these are intrinsic operations that you very often use. Or it can be a derived type IO operation. We'll see a little bit more about that. Maybe we'll have a think about this later on. But this is how we overload operations in Fortran and say there are multiple ways to do this piece of work. You, the compiler, should now pick which one is correct given the types that we are using. So we've seen this example about using an assignment subroutine to assign objects using the equals operator. But there are lots and lots of things that we can choose to do here, and we'll take a look at most of them actually just now. So we will always expect that to have one or more of these procedures in this specific procedure list. As I say, I actually mentioned this just a bit earlier. The module part at the beginning is optional because we could be talking about procedures which are somewhere else, an external function or an external subroutine. But probably if we're trying to write maintainable code, we will always try to keep the procedures that we're using here in the same module as this interface, in which case we would put module at the front of it. a question just came in. Does this overload affect the performance of standard assignment, or is it processed out by the compiler? No, so this all happens at compile time. So you could maybe say the compilation will take fractionally longer, and I really do mean fractionally, a percentage of a percentage of a percentage, just while the compiler takes a look and picks out which of the specific procedures in this list it actually has to use. But that's all compile time. When you once that's done, the actual compiled code will just be a direct call to whichever one of these is actually the correct one to use. So in terms of the performance that people really care about, the runtime performance, there isn't any overhead at all. Okay. Yes. So we've seen this before, and we've done it in an exercise. And as I said, in this case, what you have here as your procedures for assignment operations, these must always be a subroutine and not a function with two non-optional arguments. And we want the left-hand side to be intent in out or out, and the right-hand side to be intent in. And again, that makes sense. We want to change what is on the left-hand side of the equals sign and just use whatever is on the right-hand side of it as input to help work out what should be happening on the left-hand side. So on the left, we can change things. On the right, we're definitely intent out to make sure that we can't make any unexpected changes to our right-hand side. So we can do a few things with this. What we can't do is use a redefinition of assignments between intrinsic types. So what we can't do is tell the compiler, from now on, when you do an assignment between a real and an integer, you're going to do it like this. You aren't allowed to do that. Assignment between those intrinsic types is not possible to change in any way. So this is purely for doing assignments between intrinsics and deriveds, or between two deriveds. So in this case, for example, what we could have is we could have an assignment from integers using our array type again, where rather than providing it with a whole array to assign into its internal array values, we instead just provide a single integer. So if we said our array type equals whatever number of whichever integer, it would set all values in its internal array equal to that integer. So in this case, we do have one derived type and one intrinsic type. This might be a little bit confusing if you think about, okay, what happens if what's on the right-hand side is actually a whole expression? What if we're doing a function call multiplied by 10 divided by another function call? In that case, you can think that what will happen will be the whole right-hand side will be evaluated to whichever underlying type it resolves to, and then the left-hand side is being set equal to whatever is left on the right-hand side after that happens. So at that point, the compiler does actually know what type it would be, and it can work out which assignment it ought to use. So as it says here, you can kind of just think, put everything in the right-hand side in parentheses, and it will work out all of that first of all, and then say, okay, what I've now got is an integer, for example, And in that case, if it were assigning to my array t, it would use this function here, because all of the right-hand side is just evaluated to this single scalar integer. If you use an elemental subroutine, and I think people come across these less than elemental functions actually, but you can actually write elemental subroutines too. They work just the same way. You can write those as a generic interface, and in that case, it will apply for both scalars and arrays. And it may specify which combinations of ranks are allowed, and in that case, it still just lets you use intrinsic assignments for the other ones. So this is actually quite nice. It's actually fairly clever. I think the compiler is able to work out actually quite a lot here when it's trying to work out which of these overloaded operations it's actually allowed to do. It can go quite a long way in understanding that. So we can take this further. So we've said about assignments, but we can really do this with anything at all that we like. So we can create a generic interface, and we just do that by saying interface and then giving it a name. Before, I think every case until now when we've done interfaces, we haven't put anything after the interface word here. But if you give it a name here, it turns into a generic interface. So you just create it like so: interface generic name, end interface generic name. Again, as I said earlier, it's a good idea to finish off with the same name that you used at the beginning, just to make clear when you're going over this again where it starts and ends. And inside that interface, you'll be doing something like module procedure ... and then giving it the list of all the specific procedures which can be used to resolve generic name. So, for example, what you might have is interface my generic name, and then within that, say there are two module procedures, so two functions or subroutines which you've defined lower down inside this this module, and they can be called my real 32 implementation, my real 64 implementation. So they're probably functions or subroutines which do the same thing, except one does it with real 32s and one does it with real 64s. When you're writing your code, you don't have to think about which one I need to use. You don't need to remember if this one is named like so or this one is named like so. You can just call my generic name and pass it either a real 32 or a real 64, and the compiler using this interface will pick out which one it should actually be calling to do that work. So, as I say, this is a little bit of overhead in terms of compile time, and really just a tiny little bit. But in terms of actual runtime, there isn't any performance at all, because it's by the time it's compiled, it's already hard coded into the binary, into the assembly along the way, that it's actually calling either of these two. There is a quick point to note. Your procedure list here should be either all subroutines or all functions. You can't mix them. That makes sense if you think about it, because you're always going to be either doing call subroutine or just using a function in whichever way. So there would never be any case where you, as the person writing the code, would be saying, I'm not sure whether I'm using a function or a subroutine. That's something which is sort of already just the case by the nature of what you're writing. So you can't mix them, and if you think about it, that isn't actually any issue at all. As I said just a second ago, the compiler can go quite a long way to pick out which of the specific procedures it should be using to resolve a generic interface. But there are still some rules. Most of them make sense. So if you have pairs of dummy arguments inside two procedures, then you can say that they are distinguishable if they are both data objects and have different types, kind parameters, or ranks. So this one is what we saw up here, where you maybe have a real 32 and a real 64. They're both real, they're just different kind parameters. Maybe they're ranks. Maybe one is allocatable and one is a pointer. And that's actually what we would have seen maybe if we'd gone a little bit further with our array type code from just a bit ago. And also if one is a procedure as an argument or a data object. I think that all makes sense. I think the one thing that can actually sometimes catch people out, and that's what we've got down here, is that the order itself isn't actually something that can be counted on. So if you have two, in this case, this example here, let's say we have two subroutines, and one has a real arg1 and a real arg2 in that order in the list of dummy arguments, and the other one specifies real arg2, real arg1. Although those two real arguments are in different positions, they've been swapped around. The fact that they have the same names makes it difficult. It means that the compiler can't actually now tell them apart, or rather, it can't safely tell them apart. Because you have to remember that whenever you do call something, you're allowed to optionally use the keywords, like so arg2 equals y, arg1 equals x, and that lets you specify those arguments in any order at all. And with that, the safe ability for the compiler to tell two procedures apart based on purely the order of their dummy arguments and nothing else, that breaks down, and it can't safely do that. Because if you decide manually at the point of calling it, like so, to reorder it, then all of a sudden one of them could look like the other. What you do if you end up in a spot like that is you would probably, to keep things simple, just rename one of the dummies. So maybe call it arg1 to arg11, for example. Something simple that hopefully still makes sense. Just something small, so that the compiler is able to tell them apart. And finally, yes, the presence or absence of a pointer attribute in a dummy argument isn't enough either to tell them apart. That's because a pointer actual argument can be associated with a dummy argument which isn't a pointer, and that again makes sense, because what you're calling it with, it could be the underlying object, or it could just be a reference and an alias to it, which again just makes it impossible for the compiler to tell it apart. Okay, so we've come up to our first exercise here, our first example. So we're working with the same problem from before, my array type, from the array code. And what we're going to do is we're going to just see, can we overload the default constructor using the function myArrayAllocate. So we've got a new version of the code available. So let's quickly take a look at this. If we head into 05, and in here we've got this. So you were using example 1 and my array type. Let's open these so I can just show you, and then I will let everyone have a few minutes to have a go at this. So this is very much the same code as before. What we did here was we had myArrayAllocate was the function that we were using to assign to A, and what we're being asked to do are to overload the constructor for myArrayType using the myArrayAllocate function. So I think what I'll do is I'll let everyone just take 2 or 3 minutes to do this. We've seen how to do it, I think, in 2 examples now, so hopefully it won't take you too long. I'll let you have a couple of minutes to do that, and then I'll show you, and then we'll also take a look at this next little challenge here. So I'll be quiet for a few minutes while you get on with that, and then we'll see how it's done. Okay, I think that's probably actually enough time for this. It's really quite simple. So we've been seeing up here, oops, how to do this. Interface generic name, module procedure, specific procedure list. This is exactly what we need to do. So what we need to do, we are being asked to overload myArrayT using myArrayAllocate. Let's take a quick look at what we have. So here's myArrayAllocate. We've got that written. We just want to be able to use myArrayT instead of that. So let's use an interface to this, a generic interface. So let's say interface, and we give it the same name as the type itself. So what we're doing here is we are specifically overloading the default constructor of the derived type. So interface module procedure, because it's in the same module as this one, and it's myArrayAllocate and interface myArrayT. Okay, should be enough there. How do we use that? So at the moment we are creating our array with A equals myArrayAllocate. We're directly calling the function, but now we've said to the compiler you're allowed to use this to overload myArrayT. So let's just use the name of the type itself, which we've overloaded. So now we can just say A equals myArrayT3, and this should assuming nothing has gone wrong, compile. Let's just try this. Example 1.f90 compiles, and let's check it runs okay. There we go. It's worked. So that's just an example, really, of doing this or this. There's really very little to it. It's something which maybe feels a little strange if it's perhaps the first time that you've done it, but it's actually quite a simple, effective way to work. You're just telling the compiler that it's allowed to help you in this way. What we're now going to do, and we'll spend another 5 minutes on this, is to use a constructor of a new type, which is going to do the same thing we talked about just up here, where we're going to allow it to take a type and an integer number. And when it does this, it should use that that integer on the right hand side to say, let's just put all of these values into it. Let's just use this integer to initialize our array. So let's try and write this. I'll give a few more minutes for this. Again, write that new procedure to do this, and then see if you can again add it to the interface and use it. Okay, I'll give everyone a few minutes to do that, and then we'll see if it matches up with the way I would do it. Okay, comment in the chat, got a core dump, and that's interesting. I wonder how that happened. Do you want to put anything, if you want to copy your code into the chat or something, we can take a look at it. Core dump's interesting. How would it reach a core dump? How would it go that badly wrong? Presumably something in the memory. I'm guessing something memory is going out of bounds. State of B. Okay, are you able to print out if you delete B values from the end of your print statement, does it at least tell you whether B values is allocated or not? I'm guessing this could be the issue. It may not even be calling the correct allocator for you, the correct function to do this. Okay, actual function. Yeah. Okay. Okay. So the issue here, yeah, is that it won't be creating values properly. So with just the value going into it, which remember is just a scalar integer, you can't actually tell it how big it's meant. It still doesn't know how big it's meant to be. So A values would work, and an assignment of this type would work if the right-hand side were an array of the correct length. So if you could use something to tell to set the right-hand side to an array of the correct size, I would exactly, that wouldn't be a bad way to do it at all. An implicit loop. Personally, I mean, I will just show what I would do, and it's almost the same as yours. Let me just get coding, and you'll see that what I would do is really I would just use an allocate ahead of setting the values of values. So let's just an implicit loop isn't at all a bad way to do it. That would definitely work. That would definitely work. So let's do function. My array. Oops. My array allocate from int, we'll call it, and that's going to have nlen and val, and it's going to have the result of a. And so we need to tell it what we want to come in. We want that nlen to be intent in. We want a real, which is val, and that's also going to be intent in. Success now, thanks, perfect. Yeah, it's just that it wasn't able to tell how big it should be. So something slightly messy was going on in the memory there, I think. And that should be val, yes. And then our output A is of type my array T, and that's A. So we just set A percentage nlen equals nlen for argument. Then we want to allocate, or as we saw in the chat, we could also skip this and do a direct assignment using an implicit loop. I'll just use an allocate. A percentage values should be of size nlen. And then we just say that all of the values of nlen should be equal to val. And let's end that function. My array allocate int. And then all we do, we just add it up here. Just you could add it on the same line, just do comma my array allocate int, just for the sake of space. And I think it looks a little bit tidy. I'm just going to do it my array allocate int. Okay, great. That hopefully will do the job. Then let's just change it here. So let's now just try here. My array allocate 3, and let's just put values of 10 in it. So we are asking now for it to go to my array t. The compiler goes, oh, okay, so your two args are an integer 3 and a real 10. My two options are my array allocate and my array allocate int. My array allocate just takes one integer. My array allocate int uses a single integer and a real, and it will go for the latter. So it will actually use this function, my array allocate int, to do this. So let's just make sure that this works. Compile it and run that. And oh, so here we can see something. I'll actually just show this quickly. This here, 3 times 10, this is the Cray compiler being a bit clever. It's saying, okay, so your output is just 10, 10, 10. I'm not going to print 10, 10, 10. I'm going to just print 3 times 10. That can be a little strange. That can be odd to people who maybe aren't used to it. If I recompile, this is what Fortran does. You can also see Cray's inserting commas. So this is the exact same print star, but it's up to the compiler to determine how it wants to do print star. I think probably this is what most people are used to. So let's just carry on with this. Anyway, I hope that demonstrates that to everyone. Does anyone have any other problems doing that, or any questions? Nothing, I don't think. Okay, I think everyone's happy with that. Let's just work through this together, I think, this one. So let's take a look at example 2.f90. So let's just quickly take a look. Example 2.f90. So what we have here, what we've got is a module by itself. So we aren't going to compile this. So we aren't going to link this into code which can actually be run on the CPU. We're just going to compile to an object and a .mod file. Public, and there's an interface myPrint, and the module procedures in that the specific procedures corresponding to the generic myPrint are myPrint A and myPrint B. Subroutine myPrint A has arguments, dummy arguments AI. myPrint B has dummy arguments IA. In both, A is a real intent in, and I is an integer intent in. If we compile this, again, let's just do -C, so we only compile to object code. We get an error, and error message is actually kind of helpful. Does anyone know what the issue is here? You can just put in chat if you like. I spoke about this 10 minutes ago. Hopefully you can see what's going on. So think about the keyword argument case. We spoke about it just up here. I'm trying to give hints here. I'll open up the code again. I think that's most instructive. Does anyone want to shout out in chat what the issue is? Okay, so what do you want to look at? What do we all want to be looking at? Okay, not obviously. Okay, so this is hopefully helpful then. So the issue is, yes, the dummy arguments have, well, it's partially that they have the same types. That's only half of it. The real issue is that not only do they have the same types, but the dummy arguments of each type have the same name in both. So in my print A, there is a real called A. In my print B, there is also a real called A. In my print A, there's an integer called I. In my print B, there's also an integer called I. So just looking at this quickly, you might think it's fine. In one of them, they've ordered AI. In the other one, they're ordered IA. That isn't actually the case because I'll just start typing. Just imagine this is in program code somewhere. So I'll just bracket it off with some exclamation. What you could do using the interface, we could do call my print. We could do call my print A equals some real, I equals some int. And remember, now that we're using keywords for the arguments, and that's optional, it has no way of telling which one of these we actually want to use, because we've said all we said is that A is here, I is here, but perfectly valid is also if we had swapped these around and done call my my print I equals another real, another int rather, A equals another real. In both cases, we're using the generic my print, but it has no way of knowing which of the my print A and my print B these should resolve to. And that's really just because the order is entirely fluid here. There's just nothing to tell them apart anymore. It possibly could do if it were inside the same module, but we're calling from anywhere at all. We're calling from anywhere, and they're compiled independently. So from some other program unit, say in the program itself, some other module using this one, it loses that external information. The only thing it has to go on then is the interface, and the interface says you can use either of these, but who knows which one is which, because now we're doing we're using keywords. There's no way to guarantee at all which is meant to be which. Does that make sense? Please do say so if this is a bit fuzzy, if you have any questions about this. Yep. Okay, that's good. Last statement made it clear. Okay, perfect. That's good. Okay, that's good. So this is doing its job then. Okay, great. So yeah, this is slightly strange, and I think this does catch people out. And also just to say, how would we fix this? It's not perfect, but we've got to do something. For example, a really simple thing to do would be to just make that J, say, and this B, and the same here, and this J, and this B. Oops. Because now it isn't possible anymore. If we did if we did call my print A equals 10, I equals 1, there isn't any way now to mix up between this and this, because we couldn't ever use A equals something, I equals something for my print B. They are now different. Similarly, if we did my print B oops, my print B with B and J, this would now always resolve to my print B because they have different names. It seems kind of strange. This is one of the few times I think in Fortran where the actual names of dummies actually really is important. It doesn't happen often, but this is one of the cases it does actually matter. Have a question. Is this a lot of work to make the main coding use aliases and obscure actual function? It can be. To be honest, in practice, to be honest, this is slightly contrived. I don't think this happens often in real life. When you're typically doing this, the reason that you are doing the whole generic interface thing is because you do have something that is different enough in the implementation that it can actually easily tell between them. This particular case where the names are the only thing telling them apart, it happens quite rarely in general. Most of the time, when you're using a generic interface, just the sort of the circumstances in which you want to use it, it will probably be fine. Actually, these are actually what you probably want to care about more. And typically these 2 points in particular will always be different, so you can always tell them apart. The case where you've got things which are exactly the same, just different in name, you wouldn't really write different procedures for them anyway. So yes, it is a little bit of work. Probably it's not really going to happen to you. It's worth bearing in mind, but it should be very, very rarely something that you actually need to care about. That's been useful for me. Like that. You're very, very, very welcome. I'm glad it's helpful. Okay, I think we've finished with that then. So let's carry on. This is what we just did. Okay, so let's carry on with overloading operators. So we saw about how we can overload assignment, and I did say we can overload, useful mathematical operators as well. And that's what we're going to be doing here. So we can do we can use our arithmetic, our logical operators, relational operators, all of these intrinsics. We can actually tell the compiler how to use them with our derived types. When we are using all of these, then what we have to provide are always a function, and they always have to take a specific form. So if we're writing a function to act as a unary operator, then it has to take exactly one argument. Makes sense. And for binary operations, it should take exactly 2. Again, makes sense. For both of these cases, the arguments have to be intent in. Again, that makes sense. If we started adding things together and then found that the things we were adding had themselves changed, that would be very odd and probably pretty bad code, because whoever came along and used that, whether that's someone else or us in the future, they'd probably be very confused and probably have to spend a lot of time debugging that. So it makes sense that our arguments to these operators should all be intent in. Again, you can't do this for intrinsics. The only combinations are between derived types, so 2 derived types or a mix of derived and intrinsic. If there isn't a derived type involved somewhere, then you can't do the overload. So for an example, let's imagine that we've got two derived types. One is a date time t. Let's just imagine that this includes a date and a time. We'll call an instance of it now. And we have a derived type time interval t, which is just some period of time given in seconds. So what could be really helpful if we were working with this would be the ability to add them together to say, okay, I've got a date and a time. What is the date and the time if I add 5,026 seconds to it? And in that case, really similar to what we've done before, we have a generic interface, and what we're going to be overloading here. This looks pretty similar to the assignment overload, except we do operator and then inside brackets what it is that we are going to be overloading. So this actually works. I should mention the slide. So this actually works as a generic interface extension. So within the compiler itself, this interface operator plus already exists. It's already there for every intrinsic type that there is. Remember, we can't change those, but what we can do is we can add to them. So operator plus says we're going to add to plus so that now it works on everything that plus already works with, and now whatever combination goes into add interval to date time. So you can write a generic interface. I'll quickly go back up here. You can write a generic interface, my generic name, for example, and you can have as many places as makes sense interface my generic name, end interface my generic name, and start adding more into it. So you can extend a generic interface anywhere and add more specific procedures back into it to be used. So we're doing that here. We'll see how this works. So we're saying here, okay, add already works for a whole bunch of types. Now you can also use add interval to date time to do plus. We have to write that, of course. It's using our derived types here. So we say function add interval to date time, date and dt. That's a date time t, and the other one is a time interval t. Both are intent in, just as we said, and it returns a new date also of date time t. And then inside the function, we just do whatever works to actually make this make sense. Of course, that does put the burden on us. You know, we can't just tell the compiler, you're now allowed to add this and this other thing. We have to tell the compiler, this is how you add these two types. We have to say, this is what makes it actually make any sense. Once we've done that, we're now allowed to do now plus dt. And there's a couple of points here. I'm actually going to mention this first point first. This is exactly the same as doing this, and you could do both of these. Both of these mean the same thing. New date equals add interval to date now dt. This function here is exactly the same as this here. The compiler through the generic operator plus interface is now turning this into this. That's all that it's doing. This is just some syntactic sugar, if you like, to help the compiler and understand that it's able to do that. The other point to make, and this is important, is that the order of these operands is important. We've specifically done here now, which we said above was a time date t, and we're adding on the right hand side of that dt, and that was our time interval t. So because this is being turned into this by the compiler, if we had done instead dt plus now, the compiler would have looked to see, does it have a function which adds on the left-hand side the time interval, and on the right-hand side, so its argument here, the date time type, and it would have said, no, I don't. And it would have probably then thrown an error to say, sorry, you've asked me to do dt plus now, and I don't actually understand how to do that. So that means that there's another bit of a burden on you, in that if you want your code to be completely general, you have to spend perhaps quite a lot of time thinking about every combination of well, first of all, every operator that applies to any given pair of types, and to then write those, and then also to write them in the reverse order. And that isn't exactly ideal. That there is some extra work needed in that. It isn't perfect at all. And yes, commutative nature of addition. Well, if you mean commutative nature of addition, I mean, yeah, there is that. This means that it does allow you to be specific when operations aren't commutative. And actually, that's important. Just down here in our exercise, we'll do in just a second. But it just means it's so general that it requires work from us, is really what I guess I'm saying. It requires extra effort from us that in a lot of cases isn't actually required. In this case, now plus dt, it should give you the exact same answer as dt plus now. And that we have to consider them separately is kind of a little bit annoying. It's just extra work for us that, you know, in an ideal world we wouldn't have to do. So yeah, it does. So as it says in this call out, it does raise a few concerns. If you only have a single type, then this isn't an issue. But if you bring in even one defined type, then you can quickly end up with a whole lot to do, a whole lot of operations to write and to define in an interface that really does turn into just a lot of busy work, a lot of boilerplate. So doing this completely can be a lot of work. It's just something to bear in mind. What is interesting, I think, is that this introduces a new concept that we can actually create our own operators. So we do that by doing the same thing. We have interface operator, and then inside the brackets we just give it a name. That name looks a lot like older style Fortran, where we had a lot of dot thing dot. Of course, we still see it in things like trues and falses and Boolean operations. Logical operations like and, or, and the like. So we say dot add dot here. So we here what we've done is we've created a new operator called dot and dot dot add dot, and then we can just use it like this. How does this work when we need to work out the ordering of it all? Which operators have precedence? So if you're using the just the intrinsic operators, nothing changes. If you're introducing new ones, it can get a little bit messy. So what you want to do really is to use brackets. You want to use parentheses to establish which order these go in. Probably if you're trying to make code readable, probably you want to put parentheses in anyway to make sure it's easy to follow this big bit of maths or whatever, rather than just relying on precedence to work out to help the reader understand what's happening when. Okay, and leading on to this is actually what I think is quite a nice practical. It's a little bit longer, um, but this is, I think, really worth doing. I think this is something that's quite powerful in Fortran. As I say, it does require some busy work from you, but it can also help you make life easier in those cases where you maybe use these operations a lot. So for this challenge, and it's going to take a little bit of time, what we'll do is we will write a new module. So we're starting from scratch here, I think we are. And that's going to hold a normal vector, just say to a point in normal space. So it has three coordinates. We'll call them U1, U2, and U3. And they can just be integers to keep it simple. And then what we're going to do is we're going to create from scratch a cross product operation, and that's given by this little bit of maths here. I'm sure everyone here knows what a cross product of two simple vectors looks like. And you can also take that further and create a dot product, which is actually a little bit simpler, of course, that looks like this. And then you can test that out. You can just write a little bit of code to do this and test does it work. So yeah, I think my vector type is empty, and example 3.finity should show you how it works. Let's just take a quick look at that. So example 3 and my vector type. So let's take a look at example 3 and my vector type. So here's the program which we're going to be using. It uses the module, creates three my vector types. You can see that's here already inside the module. Type public my vector type contains three integers x, y, and z. What we don't have are a dot product and cross product operator. So what I'll say that we can maybe do, let's take it's 20 past 11. Let's take 20 minutes. So we'll come back at 20 to 12. And if people want to walk around, go and have some coffee or tea, or just take a quick break, stretch your legs, read your emails, we can do that. If you want to come to spend some of that time doing this, having a go at this, please do. When we come back at 11:40, I'll start working through this and talking through it. You can do the same, or if you've had an attempt yourself, you can see if what you've done in that break matches with what I will be doing. So let's stop there just for a quick break, and then we can see what people have managed in 20 minutes time. Okay, I'll see you then. I will still be around. If anyone has any questions in the meantime, please just drop them in chat or send me a message directly. Okay, I'll see you then. Okay, hi again, everyone. Welcome back. I hope you were able to have a nice quick break, waking up with some caffeine if you needed it. I definitely did. And I hope you're also able to have a go at that exercise. If not, don't worry, we'll go through it just now. Let me just bring up my screen again, and we can take a look. So, okay, here we are. I've been a bit cheeky, so I copied and pasted the solution directly across, because I knew that if I spent any time doing the cross product, I would definitely be making typos in the order of the operators and which X, Y, Z components went where. So just to save a little bit of time, I've copied and pasted that. Still, it's worthwhile me just quickly walking through this and telling you what we've actually done. Hopefully this makes sense. I don't think anything here is too far beyond what we were actually covering in the session just now. What we've done is we first of all said here are two functions which we've put into our module with our vector type. So here is our my vector t that we said we had at the start. Just contains 3 integers x, y, and z. Nothing at all out of the ordinary there. Both of these functions work as we said operator functions have to. So they are both functions. They take in 2 intent in this case, both derived types, both my vector t. So my vector t intent in AB is what we have for both the dot and cross product. And both of them also return a single result. In the case of the dot product, an integer, and in the case of the cross product, it's another my vector t. So this is working exactly as we would expect these two from normal vector maths. And we've done the calculation in both as we would expect. As I said earlier, it isn't enough just to tell the compiler that these operations exist. It's up to us to tell the compiler, what would actually make sense in them. So our dot product, we've just done the x components multiplied together, plus the y components multiplied together, plus the z components multiplied together. Cross products, of course, is a little bit more complex because we have to work out the x, y, and z components of the result vector independently from one another. But we just go through and do that for each of those, and then those are returned for each function. The only thing left to do after that is to tell the compiler that we now want to be able to use both of these functions, not just as functions, but as our new operators. So at the top we say interface operator, and we call it dot. Makes sense. A dot product. Let's just do dot a full stop dot dot. So I guess dot 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 if you like. I'll have a comment. What does the comment say? Z percentage Z looks strange. Where is Z percentage Z? Is that in the solution? Oh no, I see what you mean. Yes, it does look a little strange, doesn't it? Maybe we should have just called that result something else. I mean, we could do that. Yes, we could, if we wanted, just change this to I mean, we could just call it C or something. Might look a little nicer. It should work the same way. Still, I don't think there's anything else there that needs changing. Maybe just looks, except I've just deleted the percentage side. C percentage Z. I think that maybe looks a little less strange. I think that's a perfectly valid comment there. So yes, so we just tell it that we want to use our dot prod function as the specific procedure for our generic interface operator dot, and we want to use cross prod as the specific procedure for our generic interface dot x dot. Meanwhile, I've just done a little bit of filling out in the example. We're using the vector type. We define 3 my vector t's, I, j, and k, giving them 1, 0, 0, 0, 1, 0, 0, 0, 1 as their components, and then we just run through some prints. So we say we expect 1 for I dot I, we expect 0 for I dot j, expect k for I cross product j, I for j cross product k, and for k cross product j we expect minus I. You can see here I've had to do a little bit of work here to make this print. If you just print out minus I, that actually gets you an error. And the reason for that is that minus I requires a unary operator to negate I, which means a unary operator to negate a my vector t, which doesn't actually exist because it's a derived type. The compiler doesn't innately know how to negate a my vector t. What we could do, maybe an exercise if you're interested, is to try and write that. For now, I've just done things as quickly as possible to show you this, and then we'll carry on. So for now, I'm just printing out each component negated individually. Anyway, let's just save all of this. As you can see, I've been testing in the break time, and if we run that just the same as before, thankfully me changing C, I didn't miss anything. That seems to have worked. So for the dot products, we get 1 when we expect 1, 0 where we expect 0. And for the 3 cross products, we get the correct vectors that we were expecting to come out of that as well. So hopefully you can see how this is very helpful. It's just, if we're going to be doing this a lot, we need to make sure that, you know, particularly if we have different types in A and B, that we know, so that we provide functions for all of those, because the moment we write something we write a combination for a given operator that we weren't expecting, we introduce errors. There was the final question here, which I haven't done yet. Does a scalar triple product u.v cross w work without parentheses? So let's just give that a go. So here it is, u.v cross w is the equivalent of i.j cross k. So let's just try printing print star this exactly, i dot j cross k. Well, I think probably everyone can guess what's going to happen. We did talk about it before the break, and we have an issue. It should be pretty obvious what's going on here. This is now evaluating left to right. So we've got i.j, so a dot product that's now returning an integer. So this is first turning it into an integer type kind 4, we can see, and then that is in turn being crossed with k. So now we're saying do a cross product on an integer with a vector, and of course that doesn't make any sense. We didn't write anything to do that. We could have, if it did for whatever reason make any sense, we could have done that. We could have written another specific procedure and put it in here, and then the compiler would have said, okay, you've given me a function for an integer and a my vector t, so I will use that to do this. In this case, it doesn't make any sense at all, so we didn't bother to write that. So to make that work, we now need to specifically tell it which order it should be doing things in, and that's to do the cross product first, which resolves to another cross to another my vector t, and then that can be dotted with the I vector. And if we just check that quickly, that now works. Was it worth talking about the triple product? I mean, we can just quickly do this. Let's just quickly do a triple product as well, since we're here. So j crossed with x, which is, sorry, I'm doing this wrong. J crossed with the cross product of I cross j. Let's see how this works out. Perfectly fine, it seems, and that gives us a vector result. So something else you can actually see here, we haven't spoken about yet, I will briefly touch on it later on, is that when we ask the compiler to print out one of our derived types here, so I'm just doing print star, here this is a vector t, and this is a vector t, this is a vector, my vector t. When I'm asking it to print these out, it isn't doing anything fancy. The compiler is just going to list to vector format. It's just going to do basically a print star on each of the components x, y, and z in turn. So it isn't doing anything complex. If we wanted, we could have written a format to deal with those and make them look pretty or more informative or more usable in whichever way. Here, that isn't what we've done. I will briefly talk about this later on this afternoon. But for now, I think we've finished there. When I supply those solutions, so if you take a look here, so I don't think they're in the directory, but I may just add them. Everything that you really need is here. Would it be helpful if I did dump those into the directory as well in the repository? I think they were missed for some reason. If that's helpful, I will put those in later on today. I think I will. I'll just do that for the sake of completeness. I'll do it anyway. Let me make a quick note. And yeah, I'll put those in this evening, just so that they're there in the files themselves. So the solution here, so I literally copied and pasted this in, and then just wrote out the print statements to check, because yeah, this would have taken me a little bit too long in the time I had. Okay, are there any other questions, or shall we move ahead? We're really moving on to object-oriented coding now. Are there any questions on the material we've just done, or that exercise? Okay, so I think we're good to go. So I think Fortran, this is getting pretty interesting now. So we're really starting to take what we, fairly simple derived types that are themselves useful, but we're really starting to make them very, very useful now. And this is where, as I say, yes, we really are moving on to object-oriented Fortran in this exercise, this lesson. So what we're covering here is type extension and polymorphism, not polymorphism, which I realized was a typo in the file name last night. I've changed that. You might still see that if you have an old clone of the repository. But they give us the way to say, okay, here's a uniform way to work with something of some type. Maybe we aren't quite sure how it works in full, but we can at least be sure how some part of it works, and we can let any code work with that, no matter exactly how it's been defined. So to get started with this, here we're going to be working with this example. We're going to build this up, I think, for most of the rest of this afternoon, although it's not actually this afternoon yet, we're still 5 minutes away. Most of the rest of today, we're going to start off from this very simple object T type. So let's imagine that this is in a module somewhere, and this is quite general. When we say object, let's just imagine it actually refers to some physical object, and we're making it as perfectly general as possible. So we're saying in this case that it has some density rho, which is real, and also again, like a vector, we've given it a position of its center of mass, x3. So a3 vector again. But this is very, very general. We haven't said anything more about what this physical object is. We haven't said anything beyond it is here and it has some density. So extension of objects is like this, extension of types. So this is where we take the basic general idea and start to build on it. And this is what we call inheritance. So type, and then this new bit of syntax extends object T, public sphere T, real A, and A is here, we're saying that is the radius of this sphere. So what's happening is that our new sphere T is inheriting from object T. That means it gets everything that was in object T as well. So it builds on top of it. So if we were to create a sphere T type, and let's just call it S, then we can say, okay, there's some density. Then the density we can say is equal to, and both of these statements mean the same thing. We can access the row that came not from sphere T itself, but from the object T that it was an extension to. Because it's got that density row through the extension of the object T within it, we can access it through that. So we can do S, which is a sphere T percentage, object T, which it extended, and then row within the object T. So the row from up here. But we can also do the same thing, and it's a little bit simpler. And most of the time, people will do this. They will just say that density equals S percentage row. So because it extended object T, we can actually directly access all of the object T within the sphere T itself. What you can do is if you are doing some kind of operation where you treat all of object T, so if you were doing something with your sphere T that involved all of the object T within it, so both the row in this case and the X inside it, you might choose to use this form and talk about the object T within it. But most of the time, if you were just working with the individual parts of that, you would probably just use this shorter form, just because it's a little bit simpler. There's a question: if object T is in a library, how would I know to access row? Relies on good documentation. Yes, exactly. So this is where really, if you were working with this from a library, you would say that, assuming this is all public, which it is here, you would say that this forms part of the API for that library, and it really should tell you about things like row within it. Assuming these are public and meant to be used from the outside, it would be rather it should be documented. That's at least how a good library should be provided to people to use. If it weren't, then that would be making things difficult for anyone who wants to use it, because at that point you have no choice but to go digging in the code itself. So a good library would provide good docs, and those docs would tell you that object T has a row inside it which you are free to access and use. So it can be tricky. If it isn't well documented, then you just have to go code digging, unfortunately. But yeah, it really should be in there. It really should be there and written about in the docs. Okay, briefly worth mentioning, just in case people are coming from other languages and are used to object-oriented coding there. So in Fortran, when you extend types, you can only allow a type to extend one other type. So here, where we had sphere T extend object T, sphere T it isn't able to extend anything else. So this is what we call single inheritance. Every extended type can only extend one other type. So the way that these are constructed, so we've seen examples of default structure construction here and there this morning and yesterday, and it works broadly in a similar way. If we have a sphere T called S, and we say there's some row, these are just variables which we're creating in our code. We're just going to give them some values. Then we could put those values into sphere T our new sphere T S like this. And there is an ordering here to be aware of, which is that the components of the base type go in first. So rho is the first thing that was inside object T, and that was followed by X. And so that's what will go in first here. After that, there's the sphere T's own A. So after that, we then say that A is equal to something. Oh, I see here we've changed this. This should be A, shouldn't it? That's a typo. Again, I'll have to fix this. What you can also do is provide a whole base type to do this. So if you have an object T, first of all, let's just call it obj, and you set that up, and then you have a sphere T, and you want to initialize that, you can then provide the whole obj into that. You just say object T equals obj, and then the only thing left for you to give it is the radius, which we've said here is 2.5. Here we have given it that keyword, so this is optional. Again, much like other calls to functions and subroutines, you don't have to do this unless, for whatever reason, you want to give things in a different order than they were originally specified. And yes, and as it says here, if they have anything default, so if we had actually specified up here a default value, say for A, so perhaps we said A equals 1 as a default value, then we wouldn't need to include it down here, because that would just be set by default anyway. So anything which has a default, we can choose to leave out of the constructor. And we can do this whole process really as many times as we like. So we can have a base type, and then we can have a type which extends that. We can have multiple types which extend that base type, and then multiple types, if we wanted, could each extend those extended types. The only thing really that we need to remember is this little call out up here, that each type extension can itself only act as an extension to one base type beneath it. So you can only ever choose to extend sphere T and not sphere T and something else. So so a couple of quick things here. Let's just take 5 minutes to do this. So you should have some code, object T, object type.f90, and inside there, let's just go and take a quick look. That's in 06. So object type.f90, let's see. In here we have that object T and a sphere T, and you can see here that we have actually given these default values. What we'll do is we'll add on to this a new type, a charged sphere T. And all we're doing there is we're saying that this is an extension to sphere T, and it extends it by giving it a charge Q. So that's all in there. I'll give you all 5 minutes to do that, and then and also the next challenge, we'll do them both at the same time. And then in the main program, which is example 1.f90, let's take a look at example 1.f90. You can see here that we have some objects being created. So we've got a sphere T of various types and object T's beneath them. You can see the various ways that we are building them up from nothing at all. And just see if you can create a new charged sphere and give it a value for Q. Okay, I'll just give everyone 5 minutes to have a go at that, and then I'll quickly run through that myself, and you can see if what you've done makes sense and works with it. As ever, any questions in the meantime, please do ask in the chat. Okay, hi everyone. I hope you've all had a chance just to have a quick go at doing this. It doesn't need much code. That's part of the attraction, I guess, of sort of writing in an object-oriented style. As it encourages code reuse like this. So let me open both files, example1.f90 and also object type.f90. So got a message, compile failed when S uses object assignment. Okay, well, let's see what happens. Is that just building it as it is now? Oops. ftn object type example1.f90. Something that you've added new, S uses object assignment. Why don't you, if you put into chat what you've done, we can maybe take a quick look. I'll just quickly get on with adding the new code here. So trying to reuse everything. Maybe perhaps as I do this, you'll see where the divergence has happened. So we're creating a new type, and it's going to extend the sphere T, which already has most of what we need in it. We'll make it public again, so we can reach it from outside the module. I got the same. Is it possible there's some difference between Cray and G-Fortran? It is possible. Let me finish writing the new type, and then I'll quickly switch back to Cray. If the two of you could also try switching to G-Fortran and seeing if it works for you. That would be an interesting divergence between the two compilers. I would have expected that this should be fairly well locked down by the standard. Anything different between them here would have been slightly unusual, I would have thought. Okay, let me quickly do this, and then I'll try and do the same. So I've said that our charged sphere T is an extension to a normal sphere T. We'll say that it has a charge Q, and let's just give it a default of -1.0. So we'll say it's an electron, I guess. Or has at least one electron charge, and then we'll end the type n-type charged sphere T. Okay, yeah, let me just quickly see this as well, out of interest. So module, I'll do module load progenv Cray. Oop, I can't spell progenv. Okay, progenv Cray. That's better. Let me just try to build that again. Do I get the same? Oh, okay, that's interesting. Sphere T, object T. Oh, okay, that's interesting. I wonder why it doesn't like that. Okay, I might need to do some digging into this. I can maybe check with one of the HPE people who work here at EPCC. I'll ask about this if I have a moment later on today. I think for now, most simply, we should just carry on with progenv GNU. Most code, to be perfectly honest, is going to target G-Fortran. Cray can do some nice things. It can occasionally help you. It has some nice features to help with optimization for performance. But in terms of actual, what shall I say? Actually following the standard, most code will assume that G-Fortran is the closest thing to work with. So we'll stay with G-Fortran, and I will see if I can find out more about what's happening there later on. It may be something obvious I just can't see in the moment. But yeah, we will come back to that. So for now, assuming that everything with G-Fortran is the correct way to do it, here's our new charged sphere T, and then inside our program, we've already got a lot of code to work with object T's and sphere T's. So let's just create a charged sphere as well. So let's just do type charged sphere T, and we'll call that CS for charged sphere. It's not in line with everything else, so it could be made a little bit cleaner, that code. But just for the sake of showing you this quickly, so that's CS, and we'll use the default constructor charged sphere T, and we'll say that it's going to we'll base it on top of a normal sphere, so it will have the same row x and radius, and we'll just give it a Q of -10, for example. And then we can just start printing it out. Let's just print CS. We can do print star CSQ, print star, let's pick something from the bottom. Let's print star CSX, something from the object part of it. And let's see if that works. It apparently does. A.out. Okay, so I haven't put in the helpful text in front of it, but there's our full charged sphere T. So its density, its position, its radius, and its charge, which you can see is -10. There's its charge. So we can pick out any of the components from the earlier and ancestor types within it. Okay, so the odd behavior of the Cray compiler here aside, are there any questions about this? Maybe add standards compliance flags to the Cray compiler. It may be something that would do it. I'm not sure what those are actually off the top of my head. Do you know what they are? The order of that print all object unselected. So when we do this, this is printing everything in object T in order, followed by everything in charge in sphere T in order, followed by everything in charge sphere T in order. Standard equals F2008 for G Fortran, so C is working due to us. Okay, so I'd say that's worthwhile just giving it a quick go. Let's try this. So let's go back to this. So you think just seeing if it's anything in G Fortran itself which is doing it. Seems to like it. Still works there. Yeah, I think for this, I will do some digging in the lunch break and see if I can work this out. And as I say, maybe ask some of the HP people here if it's not something obvious. It's strange behavior. I wouldn't have expected this. So the standard would say that at least unless there is actually some bug in here that for whatever reason G-Fortran is actually happy with when it shouldn't be. This should all be okay. I can't see. Yeah, I will need to go back and dig this. I will take a look at it during our lunch break and see if I can work out what's happening there. And also try fcheck all. Why not? Let's give it a go. So warn everything. Fcheck equals all. If I can spell check. Still happy. Yeah, I think for the sake of getting through the material, we'll leave this and yeah, I'll do some digging at lunch. Try and work out why the two compilers behave differently there. Something isn't right in one of them, whether it's G Fortran or the Crave Fortran compiler. Something is a little bit out of whack. Okay, I haven't seen any other questions coming through, so moving on, we'll go on to polymorphism now. So this is where we allow a given variable, in this case it's a pointer, to point to multiple different realized concrete types. So often when we do this in other languages, we use a pointer to do that, and yeah, that is exactly what we do in Fortran as well. So what we can do is we can say let's ask for a pointer called obj, but the type that we're going to give it, this is something we haven't seen before. We actually use the word class here, which we haven't actually come across yet in the Fortran syntax itself. And we say it's going to be of class object T. And of course, we're just being careful, and we're saying that we're going to set it to null to start off with. And we can also make that allocatable if we like. Again, the difference between these is sort of how it affects copies. Are we going to do a shallow copy or a deep copy? It's essentially the difference between them here. But what we're doing with the class is this is us telling Fortran that this pointer, this or allocatable variable, whichever we're using, we're saying we want this to be able to refer both to object T and to anything which ultimately inherits from it. And there's another message in the chat about that constructor. Essentially, use the derived type construction must be the same type as the corresponding component of the derived type definition. Do not match. It's strange this thing is still complaining about it. Again, yes. To get through the material, I will come back to this, I promise. But we'll carry on with what we're looking at just here for now, and then we'll chat about it maybe after lunch or just before lunch or whenever. So let's just carry on with the pointers for now. I think the pointers are probably more commonly used here for these purposes. So as I said, when we create a pointer, obj, we're calling it here, in this way, we're saying to Fortran, okay, it can point to an object T, but it could also point to a sphere T, and it could also point to a charged sphere T, or anything else which was an extension to that. And if you want the fancy name for that, we say that the pointer is type compatible with everything in that class. So the other things, the declared type then of the pointer becomes object T, but it also has a dynamic type, and the dynamic type is the type of whatever specific type it happens to be pointing to at any given time. So here we say let's create obj again. We say it has the declared type of object T. If we then create a sphere T called S, we can point obj towards it, and in that case, the dynamic type of obj becomes sphere T. And if at any point it is unassociated, its dynamic type just becomes its declared type, object T in this case. The way that you use this now is that the polymorphic variable gets access to anything of the declared type, any of those components in it, but not of its descendants. So when we point the example obj towards S, that means that we can access any components of S that that exist within object T. So remember, sphere T inherits from object T. So our S contains everything that's inside an object T, and also anything else that comes from a sphere T. In this case, the radius of the sphere. So we can access the row inside it by just doing obj percentage row, and that's fine. And we can also get anything else which is inside obj, so its center of mass is also fine to work with. What isn't correct is anything which comes specifically from sphere itself. So in this case, the radius, because that is a component of the extended type only. We said that obj points to object T, and that means we can only use the things, the components which exist inside an object T. Anything else from anywhere down the chain of inheritances below it, we can't get access to just with a click of our fingers. There is a way to access them, which we'll see just a little bit further down, but we can't just like that do it. Let's see. Let's try and push on down here towards lunch. So let's. I think we might actually do these together, just to try and make a little bit of progress. We spent a little bit more time there, perhaps, than we should have done. So I'll just try and do this with everyone, and we'll push on down towards the exercise, which we can maybe leave as something to look at over lunch if you have a few spare minutes. So what we're now going to try and do is we're going to try and compile example 2 along with the updated object type .f90, which now has our charge sphere T. So let's quickly do this. Let's actually take a quick look first at example 2 .f90, and we can see what we're doing. So we're saying here now we have a polymorphic pointer, and we're saying that it's pointing to anything which is object T or which inherits from object T, and we're calling it P. And we create obj S and CS, each of them building on top of the previous one in the chain. We point P to obj and say object density P row, PX, PA, okay. P points to S. What happens here? What happens here? So if we compile this, let's just give it a quick go. So object type .f90, as well as example 2.f90, and we get some errors. And let's take a look at what they are. Print star object radius P percentage A. You can't do that. It says A is not a member of the object T structure. That makes sense. But then we also get this for sphere and for sphere charge. What we're told is that all of these do not work. It only really makes sense for the first one. It makes sense. So an object T doesn't have an A. So when we tried to print that out, that's fine. That makes sense. What maybe doesn't make as much sense, at least at the start, is why we get the same errors for things not being members when we then point P towards a sphere or a charged sphere. Because we go, okay, wait a second. My sphere does actually have a radius A. My charged sphere does actually have a charge Q. Why can't it point at them? That's simply because what we were just saying, because we said that P was a polymorphic pointer of class object T, then directly we can only access the things which are in object T's. And if you think about it for 5 minutes, this does make sense, because the compiler has no way really of guaranteeing that at any point, if we were pointing P at any extended type, it would be able to access any given members. All we've said is that it's pointing to things which are object T's or like object T's, if you want to think of it that way, things which sort of fit in the same general shape as an object T. But that means that the only thing the compiler is happy about is using object T, is using things pointed to by P as though they were object T's, even if they're actually an extended type. So when we say, first of all, let's do P points to object, these two are fine. And moving on to the second challenge here, where it's asked us to comment out the things which are breaking the code. So let's first of all comment out this line, because objects don't have a radius here. They only have a density and a position. Our issue here, P is now pointing to S. Okay, and that works fine. We can access the density and the position. What it's not happy about is the radius, and that's because the radius is only coming from the sphere T, but as far as the compiler is concerned, it's still working with something that's really an object T only. Same thing happens here. Sphere charge, no good, because it's a polymorphic pointer of class object T, and object T's don't have charge. So that should now compile and run, and that does, thankfully, because now we're only using the pointer to access the object T parts of each of those types. There was one more little question here. Why can't we just declare the pointer to be class charge sphere T? And what's the error if we try? Well, let's just have a quick go. So let's make the pointer charged sphere. Sphere T, and try to compile it, and we get some more errors. Different types and pointer assignments. One attempted assignment of type object T to class object type class object type charged sphere T P. So you can see it's a pointer as well. It's adding on the end. This is saying you can't have a pointer to a type which is further down the family tree, if you like, of the different types, then point to something higher up. So what you have to have is it point to either a base type or the type which is the ancestor of all of your other types. If you set your pointer to be a pointer to one of the types part way down, and then you start trying to point to types which are higher up in that family tree, that set of ancestries, that's now creating problems, because this would then theoretically, if this were allowed, open up the possibility for you to start talking about things like the charges of your object T's or your sphere T's, and they don't actually exist. So again, this makes sense when you think about it for a few seconds. It's just something to bear in mind. Okay, very quickly before we stop for lunch, just a couple of minutes this will take us, is type selection. So we saw there that there are issues if you try to access the components of the extended types, which inherit from the type which you're actually using for your polymorphic pointer. And that can be an issue, because of course sometimes you might say, okay, well, I have my pointer and it's pointing to either object T or something which inherits from object T, and depending on what type it actually is, I might want to do something with it. Perhaps I work out later on that my pointer is actually pointing to a charged sphere T, and in that case I want to do something with its charge. From this little snippet of code here that looks like that might not be possible, but you can actually do that, and you do that through the type selection construct. This works very similarly to a select type, a select case construct, which you probably all know about. We just build it instead on top of our pointer. So we say select type, and then in brackets give it the name of the pointer, of our polymorphic pointer, and then just say if the type is, and then give it one type, or then we can also say class is, and then give it another type. Then we can tell it what to do in each of those cases. We can also give it a default case to do if everything else fails. There's a particular difference between these two. So if you've got a type is block and those are checked first, then it sees if the dynamic type of P is actually, in this case, a charged sphere T. When you then move on to checking classes, it doesn't just check that that the dynamic type matches that type that's given in the brackets here. It also checks whether it's any descendant of that as well. So if you like, and this holds really throughout Fortran. When you talk about types and classes and what is the difference between a type and a class, you can think that types refer to specific concrete types, and classes refer a little bit more nebulously, both to a type and potentially any type which inherits from it, any type which is a descendant of it. So when we come in here, we first of all check any and all types. Type is this, type is that. If all of them come out as false, then we start checking class is this, class is that. And if any of those, so if all of those come back false as well, then we go into class default and do something else, if, of course, any of these actually are present. What's specific about this is that the moment we go into one of these blocks, the moment that we've said type is charged sphere T or class is sphere T, the compiler is then allowed to do what we couldn't before. It's allowed to start doing this. The compiler is allowed to start accessing those components of those extended types. A quick comment, if P is not a defined type, i.e. just an integer, does the cascade fail? This wouldn't actually even compile, I think, in that case. So you mean if you set P to a pointer of an integer, do you mean? It would, yeah. Yeah, so P, so the way that you should always be creating them would be like this, and I don't think you would even be allowed to do it for an integer. I think you would always have to work with a derived type, but it would always have a defined type. So as long as it's pointing to something, by which I mean either null or else actually one of the real types that have been created, it will be pointing to something. If the pointer is actually undefined completely, then that's probably going to cause a whole lot of other problems that you would see before any of this even really is of concern. Okay, yes, very, very quickly, there are just two more type inquiry functions to mention, which you can always just do. You can ask if I have two polymorphic pointers or polymorphic allocatables. You can say, is one of them an extension of the other? which returns true or false with extends type of. And you can also ask, are they the same type as one another, true or false? Okay, so that's a little tiny bit rushed there towards the end. I think we were talking a bit too long about compilers. Sorry, that was my fault earlier on. So we have another exercise here. It shouldn't take too long, but going back to object type.f90, we can take we can write a new subroutine in there, which takes a single polymorphic object t pointer, and then going through something like this using a select type block, prints out anything which is relevant. So what we had before was all of this, where we were trying to print out everything, anything, no matter what. And of course, that wasn't actually working because sometimes these components don't actually exist. So let's try and write a function, sorry, a subroutine inside the module that will do this for us. It will take in a class object t pointer, and then say, okay, is it an object t? Is it a sphere t? Is it a charged sphere t? And then inside that, print out the things like the charge, the radius, and so on. And we'll see that way how this helps. And we'll maybe leave this for now. I think really nice. So if over lunch you're able to have a quick go at this, that would be brilliant. Otherwise, I'll quickly go over it at the beginning of our next session. Yeah, say we've overrun slightly, but let's break for lunch now for 50 minutes, and let's come back again at 1:30. Same as sorry, not same as yesterday, same as Monday. And we'll get started again. We'll cover this, and then I think afterwards we're moving on to type-bound procedures. So at this point, it is fully object-oriented code. So hopefully that'll be fun. Hope you enjoy your lunch, and I'll see you, yes, in 50 minutes at 1:30. In the meantime, yes, I'll go back and do some digging on what Crayon's G Fortran were doing differently in that build. Hopefully I'll have an answer for you at the end of lunch. Okay, I'll see you then.